Okay, hi everyone. So getting back onto my last video. So if you noticed that like my last video, like my entire audio was muted. I'm really sorry guys. But basically just to recap on what we talked about. So we talked about projectile motion, about free fall, we have talked about that weight, motion due to uniform velocity in one direction and uniform acceleration in particular direction. And then gravitational GPE in a uniform field, we know that... Oh, actually, this is what we're going to talk about. Gravitational GPE in a uniform field, that from the definition of work done by a force, this equation, GPE, change in GPE equals to mg times change in h, for GPE changes in a uniform gravitational field, like for example Earth's surface, and we use this equation to solve problems. And lastly, we're going to talk about the effects of air resistance and describe qualitatively, with reference to forces and energy, the motion of the bodies falling in a uniform gravitational field with air resistance, and including the phenomenon of terminal velocity. Okay, so let's move on to page 10, which is we're going to talk about, and we're going to extend it till page 19, so bear with me for a second. Okay, so GPE uniform field. So GPE of an object is the energy it possesses by virtue of its position in a gravitational field. Now if you consider a body of mass being lifted from H1 to H2, okay, imagine H1 here, H2 here, on the surface of the Earth. So there would have to be an external force that is equals and opposite to mg, which is weight, that is applied to the mass. So how do you do this? Like realistically, you have to move the object very slowly so that it can be modeled as an equilibrium with a constant velocity. So remember, constant velocity. Okay, so since you move it very slowly, we see that there's no change in kinetic energy. Ke equals to 0. And the external force is equals to its weight, which is mg, or what we like to call gravitational force. So you know that there is going to be no change at all. So the work done by the field, the gravitational field, and you add up the work done by the external force, it's actually going to be equal to 0. Why? Because imagine that this is negative and this one is positive. If negative and positive, if they are equals in magnitude, then it's going to get 0. So the external work done by external force is going to act upwards. You can see here. Meanwhile, the work done by the field, the gravitational field, is downwards here. Okay, so if you were to put in the values, it's gonna be the negative change in GPE plus the work done by external force. And so let's rearrange them so that they looks like this. They're the same, equals basically. Since the work done by external force is external force times change in h, this is work done by force. Remember, that's the formula. Then we're going to put in this. And so this is equals to change in GPE. And you know that external force is actually the guy's weight, the only force acting on it. And so this is how you can prove that change in GPE equals to mg, change in h. Okay, so this is really simple because there's only one example illustrating this. So imagine you have this weight, and it's lifted by a vertical force, your external force, of 7 newtons to a vertical distance of 2 meters. This means that there's going to be work done, because work done in the same direction of displacement. So they ask work done by a lifting force. Okay, so the lifting force is 7, right? And the distance it travels is 2. So you're just going to multiply that, get this. Then what about change in GPE? So remember that change in GPE is just negative work done by gravitational force. This change in GPE is going up, right? Imagine it's going up. But the work done by gravitational force is working against the guy. So that's why there's a difference in direction. And so you put in the values, which is -5, and this is travels. Why -5? weight is acting downwards. Meanwhile, change in GPE is upwards. And so always try to make it, try to follow the convention that you've made yourself, which is assuming that going upwards is positive. Okay, so this is plus 10 joules. So this means that the energy is not only to work done, because you see, it's not all 14 joules just for the work done by the force. It means some of the energy is transferred somewhere else. For example, it can be transferred to air resistance or kinetic energy if it's not moving at a constant velocity. So, last question. Assuming it was initially at rest, u equals to 0, calculate the final speed of the mass. Final speed would be this. Okay, so by conservation of energy, I like to write it this way, the initial total energy plus work done equals to final total energy. Why is that so? So we just assume that the final total energy is just, it's always like initial equals to final. But why do we have work done? Because according to this question, we've already made some changes. We give some of our energy to the work done. And some of the energy we give our energy to work done, and some of them is lost. So like that means the work done is going to be 14, right? Which is what we found here. But the other side is going to have to add up to 14. But some of it is not going to be all the way given to work done. It's going to be given to some other things. And so it's not going to be 14 equals to 14. Okay, so basically, it's either air resistance or KE, right? So we know the formula of KE is half mv squared. So that means we see that it has speed. Okay. So initial total energy is going to be 0. Because again, remember, it's initially at rest. U equals to 0. Basically, KE is 0. That means no energy. No initial energy until this guy gives a force. That's the work done. Okay, so we already found 14. Now, what's your final total energy? Final total energy is the actual product of the change in GPE. That's the result of it. Plus 10. We missed the 4. Where's the 4, right? So the 4 is given to the KE. You plug in the formulas. Remember to change your weight into actual mass. And that's why you did this. Basically isolate the V. And moving on to the effects of air resistance. So, air resistance, or what we call drag force, or viscous force, or viscous drag, acts on all objects moving relative to the air. So that means the speed is not the same as the air. Okay, so viscous drag, by the way, is a type of drag force, referring to this, like your honey, oil, and the reason why you have the drag is because of its viscosity. If you look at oil, if you look at honey, they're very viscous. Then viscous force, what's the difference? It's basically just a force caused by the fluid's internal friction. The fluid's internal friction, and this is what we refer to as viscosity. So basically, it's to resist motion between the fluid layers, or between the fluid and surface. Okay, and air resistance is also a type of drag force, like this, and it's caused by air acting on a moving object, which is drag force in air, given for moving objects. Okay, then lastly, your drag force is what you call resistive force, acting opposite to the motion of an object through a fluid, either air or liquid. So drag force is something that's more general. Okay, so some facts about drag force. Drag force always acts opposite to the object's velocity. Let's say this guy is going this way, drag force is going to act this way. Sorry, I got cut off. Okay, so basically another fact about drag force is that the magnitude actually depends on many factors. Like the shape of your object, speed of the object, and viscosity of the air. So the shape of the object. Like, car manufacturers actually spend a lot of time and money researching on the best shape for a car to reduce air resistance. Speed of the object, velocity air, actually affects drag force also. So the faster it moves through the air, the greater the resistance. And so it's modeled by this, and depends on the conditions. And actually, this is for slow objects, this is for fast objects. Just additional information. Lastly, viscosity of the air, which is affected by the temperature of the air. So the higher the viscosity, the greater the air resistance. So besides air, force, viscosity just means like it's hard to move, you know. Okay, so drag force is also present in an object moving in any fluid, which includes gases and liquids, not only air. So considering an object of mass m falling vertically from a great height, from rest, that means u equals to 0, no initial energy, near the Earth's surface, a downward gravitational force or weight acts on it. The drag force F depends on the speed of the object. So let's analyze this. Initially, you would have it start from the rest. So at t equals to 0, v is equals to 0, and that means force acting on it is 0. That's like the very first instant. And until you see that at t1, v starts increasing, right? That means drag force starts to increase also. Then this increase, this increase, this increase, this increase. So they show a directly proportional relationship until you reach t4, which is going to be its maximum velocity. So your maximum velocity is what we like to call terminal velocity, when the maximum drag force is equals to the weight, which is the same magnitude of arrow. And after that, the v is going to be constant all the time, keeping in terminal velocity. And again, force is constant. Drag force is equals to weight. Alright, so between here and here, the resultant downward force is equals to weight minus drag force, or mg minus drag force that is larger than 0. Between this. And from Newton's second law, we know that acceleration equals to F net divided by m. F net is what we established here, weight minus F. Weight is the bigger guy here. And so you plug in W minus F. Then you know W divided by M equals to G. That's why you have G here. And you're just left with negative F over M. Okay, so the resultant downward force causes the object to accelerate and the speed to increase. Let me repeat again. The resultant downward force causes the object to keep accelerating and its speed to increase. The larger the speed, it leads to a larger drag force F, as you can see from this entire thing. And so that means resultant force and acceleration actually decreases with time. Okay, so let me repeat again because it's going to take quite a long time to actually understand the sentence. So the resultant downward force causes the object to accelerate and its speed to increase. And so imagine you go from here, it's stationary, until it starts actually increasing until terminal velocity, right? That means this object is accelerating. And the larger speed, you see, it produces larger drag force. And so that's why F net and acceleration is going to decrease with time. Like the object will accelerate, but because of drag force, the resultant force is going to decrease with time. And hence acceleration decreases with time because of this drag force thing. Okay, so from 0.4 onwards, which is when terminal velocity starts to hit, that force is equals to weight. So that means F net is 0, and so the object stops accelerating. A equals to 0. So that means the star will travel at a constant maximum velocity that we like to call terminal velocity. Okay, let's move on to displacement time, velocity time, and acceleration time graphs. So these are the graphs of an object falling from great height in air. So once the terminal velocity is reached, displacement time graph is a straight line, and this is when acceleration is going to be 0 because it's moving here. Constant maximum velocity known as terminal velocity. Alright, so for displacement S, let's assume with air resistance for the rest of the graphs first. Okay, with air resistance, it starts to increase, right? As it is slowed down, like kind of slowed down by the air resistance. So it's going to be lower than the blue graph. Because it's supposed to go farther, but because there's air resistance slowing down, it doesn't go as far. That's why displacement is lower than the blue graph. Then you see after you reach terminal velocity at this time, here that there's going to be a straight line. Why? Because the object is moving at terminal velocity. So same displacement each time interval. So that's why it's a straight line. Okay, but what about there's no air resistance? If no air resistance, okay. So we use this equation right here. You notice that G is going to be 9.81 negative, by the way. And U, assuming U is 0, T is going to be squared. Hence, it is a quadratic equation. That's why it's more like a quadratic, half-baked quadratic equation. It's supposed to look like this, right? But it just cut it off. There. Then, moving on to velocity time graph. Alright, so with air resistance, you see that velocity is like 9.81 gradient. Like a straight, sorry, I did not mean that. So initially it's a straight line graph, quite a constant acceleration, right? Like there's no effect of drag force yet, or air resistance yet. But then as it starts falling down, it starts decreasing. Like the velocity doesn't go as fast anymore because there's air resistance, causing it to slow down by air resistance, okay? Because without air resistance, it would have just gone like normally, Should have had like constant velocity. But because of the air resistance, it limits the guy until somehow weight is equals to drag force. And that's when you reach terminal velocity. Okay, this is approaching terminal velocity, by the way. But if without air resistance, it would have been this. My straight line graph, okay, refer to the equation again. V equals to U plus GT, U assuming is 0, G is 9.81. Here the T is just casual T, so it's a straight line. It's a normal Y equals mx plus C graph, hence constant velocity. Not constant velocity, but increasingly, like constant increasing velocity. Okay, then lastly we have acceleration time graph. So this is very simple because, okay, let's talk about without air resistance first. Without air resistance, then A, acceleration or free fall equals to gravitational field strength, which is 9.81. This is constant, always that. But if there's air resistance, the gradient is slowly decreasing until it becomes constant to 0, which is when it hits terminal velocity. It's 9.81 until it starts decreasing to 0. Okay, y'all, we're back to example 5.3. So this purpose is, by the way, to calculate terminal velocity, test you what is terminal velocity, right? Make sure you understand. Okay, so the mass here is 3 kilograms. Falling vertically from rest, U is equal to 0. Air resistance in newtons is given by this equation, where V is velocity in meters per second. Okay, so they want to determine the maximum velocity of the object. Maximum velocity of the object is going to be the terminal velocity when the air resistance is equal to the weight of the object, or drag force equals to weight. And so R is equals to weight, and you plug that in, and plug the fact that W equals to mg. And then you just plug in the values given by Q and the known values, and then you get V equals to this. This is the maximum velocity of the object. Okay, so then we find out the acceleration of the object when the velocity is 12 meters per second. So 12 meters per second, we plug in the values again, and we find out that 7.2 newtons is the resultant force. And so again, acceleration is F net divided by m, and resultant force is going to be weight, which is going to be the bigger guy, minus the air resistance acting on it. So this is the acceleration. W is larger than air resistance, so that you have net force. So then you get actual acceleration. Okay, so this is the last example, by the way, guys, so just bear with me right now. Okay, the effect of air resistance on an object turned vertically upwards. So imagine that a ball is thrown vertically upwards from ground level with speed u. The time of flight for the upward motion, like moving away from the ground, is tu, and the downward motion, which is returning to the ground, is going to be td. And assume the air resistance is not negligible. That means there's drag force or air resistance. So explain whether td is less than tu, or td equals to tu, or td larger than tu. So from what we know, it's going to take a... Actually, I have no idea, but... Okay, if in the last answer is TD is going to be larger than TU. Because I think air resistance is going to actually die. Okay, so why is that, right? So imagine at a given speed, the net acceleration force here, when the ball is moving downwards, is less than the retarding force when it is moving up. Okay, so I don't understand this. Okay, it's fine. Sorry. Imagine this is the ball, right? So at a given speed, the net acceleration force when the ball is moving downwards. Okay, the ball is moving downwards, right? So velocity is moving downwards. This is the weight, this is the small f acting opposite to the guy. You see that you put in the values of acceleration, which is f net divided by m. G is acting downwards, and f is acting opposite. That's why it's going to be negative. Then what if, like, this guy is moving up, right? That means drag force is acting opposite to the direction of motion, and weight is acting in the same direction as the drag force. And so, if you put in the values of acceleration, which is f net divided by m, g and f is moving in the same direction. So that means you add them up. So you see that the net acceleration force when the ball is moving downwards here, where v is downwards, is actually smaller than the retarding force when it is moving up, when the v is going up. Because this one is negative, this one is adding up. Obviously it's going to be bigger, right? And so when the ball is moving downwards, there is going to be a smaller average acceleration. So the smaller average acceleration will lead to a lower velocity when it returns to the ground. Smaller average acceleration, that means lower velocity. doesn't increase as much. Okay, so if you want it mathematically, this is one of the equations. And you isolate A, you get this equation. So if A is smaller, and assuming S is constant, displacement is constant, initial velocity also constant, you see that velocity at the end will decrease. That means lower velocity. So the average speed moving up is going to be greater than the average speed moving downwards. Since the distance S is moving up, this guy is thrown up, and moving downwards are equal because they travel the same displacement. Use the formula here. We find out that the average speed moving upwards times tu is here, and average speed moving downwards is smaller. And so to compensate, the one that increases, is bigger, is going to be smaller. The one that is smaller is going to be compensated by the time, which is going to be bigger. That's why TD is going to take a longer time. Okay, so you see how they explain using formulas, right? Okay, then you're going to sketch the variation with time of the velocity of the ball. Remember that there's effect of air resistance. So this is going to be, okay, so if you remember acceleration time graph, it's supposed to be constant, right? But, velocity in time. So it's supposed to look like this, with 9.81 gradient, and some reason, right, it hits 0 when it is momentarily at rest and continue on. That's without air resistance. But with air resistance, it's going to be a curved graph. So this is approximately what happens. It's a curved graph because changes to drag force is incremental. That means it's going to be keep increasing, and adding on in the area of the series. So as it increases, because it keeps getting big. Like as it's thrown upwards, drag force starts to slow it down even more because it's moving even faster sometimes. And also the numerical value of the gradient is always going to be decreasing because it's slowing down. So imagine the ball is going up, right? The resultant downward force decreases with increasing height. Because as it goes up, the ball is slowing down. That means resultant downward force decreases. Oh wait, my bad. So imagine the ball is moving upwards. The resultant downward force decreases with increasing height. Then when it moves downwards, the resultant downward force decreases with decreasing height as the ball speeds up. Okay, I need some time to digest this. Me too, honestly. Okay, so let's skip this part first later on. So basically, the graph will end with a lower speed because the average speed upwards is larger than the average speed downwards. It starts to slow down, right? We've already established that in A. And then areas of the left and right of V equals to 0 are going to be equal because they have to cancel out, meaning same distance traveled. Okay, so this is going to cancel out each other. Okay, so basically, A is going to be really confusing, but this is what I found from ChatGPT. So imagine the ball goes up. Gravity is going to pull it down, right? So that means air resistance or drag is going to push it down. Because as it's moving up, air is going to push it down. So that's the nature of air resistance. And so the total force is slowing the ball. It's going to be both gravity, with its own weight, and the drag. And so it's going to slow down quickly and reach the top in lesser time, just du. And whoop, it has the max, and then it reaches the highest point. That's the entirety of this ball going up scenario. That's why the acceleration A equals F net divided by M is going to be negative W and negative drag force over M. It's going to be G plus F divided by M. It's large and going to be downwards. That's why the ball is going to slow down fast and reach to the highest point at a shorter time. But as the ball goes down, the gravity is going to pull it down, right? But air resistance now pushes up. Because as it's falling, air is still going to oppose any kind of motion wherever they start going. Okay, but air resistance is like your biggest damn enemy. And wants to make you fall. It's going to oppose every single thing you do. And so that means the total force is going to be gravity, its own gravity, net minus the drag force acting on it, which is the opposite, right? That means the ball is going to accelerate slowly. It's going to fall slower, right? That means this guy's going to take a damn long time to reach the ground. And so TD is bigger than TU. That's why acceleration now, plug in the formulas, W is opposite to drag force, and so drag force is just going to be a different sign. So yes, acceleration now is going to be smaller than gravity. So the ball, the drag force is going to be smaller than gravity. And that means the ball doesn't speed up as quickly. Okay, so this is how they demonstrate that TU is going to be shorter and TD is going to be longer. It will take a longer time. However, the speed here is actually higher at initial than at final. Because it's going to reach at the top, or reach when V equals to 0 quite quickly. V equals to 0 is when it's momentarily adverse, by the way. It reaches the maximum point, and it's going to take a damn long time. That means velocity is small after it reaches the highest point, when it starts to go down. Okay, so you see that it starts to be like this. And then somehow it's going to stop here, because that's when it hits the ground. Okay, so let's rethink and go back here again. So up, the resultant downward force, okay, imagine this ball going up. The resultant downward force decreases with increasing height as that ball slows down. So the ball is going to reach the top really quickly, right? At a short time, but as it slows down, the resultant downward force decreases. Because you see here, it's going to kind of decelerate, like it's going to be like really fast as it's launched, but like decrease a bit, as it reaches the top, because it's going to be like whoop, 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 wow. Get what I mean? Then it might go downwards. The resultant downward force decreases with decreasing height. And so it starts to speed up, right? It speeds up. Then the resultant downward force decreases with decreasing height. Okay, so last video, by the way, it's a bit confusing, right? We didn't understand what this two sentences mean. But I found another way. Okay, so this is the same, just let this be resultant downward force. This too, resultant downward force. So when the ball is going up, weight is going to be in the same direction as resultant downward force. That's why it's positive. But the drag force is going to work against the downward force. So the drag force is going to work opposite to the resultant downward force. That's why it's negative. Okay, so with increasing height, drag force is going to keep increasing, right? As the ball slows down after it's being after you know that drag force is increasing, that means the ball is going to slow down, right? And so when this value gets bigger, this value is going to be smaller. So imagine when it goes down, right? When it goes down, the drag force is the same direction as drag force is going to be acting in the opposite direction. Wait, drag force is supposed to act. Okay, so this guy is moving down, right? Drag force is going to, okay, my apologies then. Drag force is always going to be opposing the actual direction of motion, the V. In this case, when it's going down, the V is not going down, right? So F, drag force is going to work opposite to it. Oh, then I made a huge mistake. It should be minus. My apologies, everyone. So, okay, now repeat what I said. So when this is increasing, in increasing height, right, the ball will slow down because drag force is increasing. And resultant downward force is going to be decreasing mathematically. And so with decreasing height, as it goes down, right, the force is going to keep increasing. The ball is supposed to speed up. Apparently, I don't know. But basically when it increases, it's going to be decreasing until it reaches to the point where weight is equal to F. And so this is when the ball speeds up and reaches some terminal velocity somewhere. Because as it speeds up, it's going to... Wait, what? Okay, let me get back. Okay, so I think I found a way to explain this really weird sentence. So basically, hear me out. When the ball is going up, that means this guy can go against gravity. So imagine gravity is going downwards and air resistance is also downwards. Because it's always going to oppose the direction of motion, which is V that's going upwards. Okay, so the total downward force, or resultant downward force, is going to be the gravity and the air resistance. Both of them are going downwards, right? But as the ball goes higher and higher, you notice that it slows down. Why? Because speed is decreasing, right? That means air resistance, which kind of just always reacts towards speed, is also going to decrease. And knowing that gravity is also constant, that means the total downward force, which is gravity and air resistance, is going to decrease with height. Because you notice the air resistance decreases because the speed decreases. So that's why resultant downward force will decrease with increasing height as the ball slows down. But then when the ball is coming down with gravity, which is downwards, and resistance is going upwards. Why suddenly upwards? Because it's going against the motion, which is going down, or V is going down. And so the resultant downward force, which is gravity minus the opposite, air resistance, as the ball falls, it will speed up. So imagine that the ball falling down, you notice it speeds up because you notice the air resistance is going to keep increasing and increasing as it falls down. Meanwhile, gravity stays constant. So knowing that the resultant downward force decreases because, okay, bear with me, air resistance increases, it's getting bigger, it's going to slow down the sky. And so the net downward force decreases. And so that means, imagine downward force decreases and air resistance is getting larger. So that means air resistance is going to be subtracting more from gravity. And so the resultant downward force is going to be smaller. And that's why resultant downward force decreases as with decreasing height as the ball speeds up. Like it wants to speed up, but then it can't speed up because there's air resistance acting on it. Because it's getting bigger and the